This is a review for the Chapter 3 test, and I'm going to go through some of these problems with you and just make sure that I explain them so you can come back and watch this video as much as you need in order to prepare for the test. The first section we're going to look at is on continuity and differentiability, and I will record each of these videos in different segments so that you can watch one segment at a time that you need to watch. The first question says the graph of a function f is shown above. Which of the following statements about f is false? So if we look at it just to get a bare idea of what is being given to us, we have this x value of a, and there's a hole in the graph at a, and there's a point somewhere else. So the first one says a, f is continuous at x equals a. Well, yeah, that's not true. F is not continuous at x equals a. So that one is false. So let's come back and make sure that that's actually the one that we think is false. So we'll put a little tentative circle around it and then come back to it as necessary. B, f has a relative maximum at x equals a. If we look at this graph and look up here at the function, the fact that there is a higher point here than the ones around it means that it is a maximum. It is higher than the ones around it. So yes, it is a relative maximum at x equals a. Part C, x equals a is in the domain of f. Yeah, because there's a solid point. So the fact that there's a solid point somewhere on this line means that it is defined at a, therefore this point is in the domain. Part D, the limit as x approaches a from the left and the right are equal. Yep, they both equal the same y value. A hole does not affect the limit existing. And last but not least, the limit as x approaches a exists, and that's true as well. So the only one that is false is answer choice A. This function is not continuous at x equals a. The next question says, let f be the function given by f of x equals the absolute value of x. This is a non-calculator question, but you should have a general idea of what the absolute value of x looks like. It is an absolute value function, so it looks like that. It says, which of the following statements about f are true? F is continuous at x equals 0. Yes, that is a true statement. It is continuous because I can draw the entire thing without ever lifting my pencil off the paper. So yes, 1 is true. The second one says that f is differentiable at x equals 0. Well, that one's not true because there is a corner, so a train would derail if it came along these tracks. So a corner means it's not differentiable, therefore 2 is not true. The third one says f has an absolute minimum at x equals 0, and that is also a true statement because this is the lowest point on the graph, so it is a minimum on the graph. Therefore 3 is also a true statement. 1 and 3 would be answer choice D, so that's correct. Next question. Now you might not know what this function looks like off the top of your head, but I want you to be able to graph it in terms of plotting some points without a graphing calculator. So it says let f be the function defined by f of x equals the square root of the absolute value of x minus 2 for all x. Which of the following statements is true? If you just start plugging in points, so for example, if I plug in 2, for example, just because I know 2 is going to give me a square root that actually works. If I plug in 2, I get 2 minus 2 is 0, and the square root, one second. So if I plug in 2, let me make a little XY chart over here. If I plug in 2, I get 2 minus 2 is 0. The square root of 0 is 0. So let me start to plot some of these points on the graph. So at 2, it equals 0. Then another square root that would be a nice square root is 1. So let's see what we would plug in here to make this equal 1. If I plug in 3, 3 minus 2 is 1. The absolute value of 1 is 1. The square root of 1 is 1. So at 3, it should equal 1. Another nice square root would be 4. So in order to make this equal 4, I would plug in x equals 6. If I plug in 6 here, I get 6 minus 2 is 4. The absolute value of 4 is 4, and the square root of 4 is 2. So at 6, it should equal 2. So I hope you have an idea of what it looks like on this side. It's starting to look like the square root graph. The absolute value has not affected it at all with these numbers that we've plugged in. So this is looking like the square root graph. Now here's how the absolute value does affect it, is the fact that we could go on the other side and the absolute value would take care of those. So for example, if I plugged in numbers less than 2, Like, for example, if I plug in -1, I get -1 minus 2 is, sorry, not -1, +1. If I plug in +1, I get 1 minus 2, which would be -1. The absolute value would take care of the negative and make that a +1, and the square root of +1 is 1. So it goes through the point 1, 1. And I hope that it's pretty apparent that it's actually going to start to be an absolute value, making the square root go the opposite way as well. So let's plug in one more number to show that that's true. So earlier I plugged in 6 to make this equal 4. If I wanted to equal 4 in the other direction, I could plug in -2. If I plug in -2 up here, I get -2 minus 2, which is -4. The absolute value of -4 is +4, and the square root of +4 is 2. So over here at -2, it equals 2. And again, that's what the graph is going to look like on this side. So now that we have an idea of what the graph looks like, and again, I wouldn't expect you to know that off the top of your head, but I would expect that you can at least kind of come in and plug in some points and figure out what the function looks like based on that, kind of figuring out patterns. So we can come up and answer this question now. A says f is continuous but not differentiable at x equals 2. That is a true statement. We can draw the entire thing without ever lifting our pencil off the paper, but this is a cusp, meaning that it is not differentiable. So I think A is the correct answer. Let's go through the rest to make sure. B says f is differentiable. Nope, because there's a cusp. C says f is not continuous. Also not true. We just said that it is continuous. There are no undefined values here. The limit as x approaches 2 does not equal 0. That's false. The limit does equal 0. Both sides go into 0. X equals 2 is a vertical asymptote of the graph. Also false. This is not a vertical asymptote. They both come in to be 0 on both sides. So the only one that was true was A. For the next question, it says, let f be the function defined above. Which of the following statements about f are true? So the first one, f has a limit at x equals 2. So remember that this is the kind of graph, it actually doesn't have a breaking point. It has a hole in the graph. It says this is the function it equals everywhere except at x equals 2. And then at x equals 2, it happens to equal 1. So if we want to know what this graph looks like, let's figure out the limit of what it's going towards. So I can take this top function up here and factor the top and bottom to figure out where my hole is. So that would be x plus 2x minus 2 all over x minus 2. And then my hole is at x equals 2, so I can get rid of that hole, and the limit would be going towards, or the function I should say, looks a lot like x plus 2 except for that hole at 2. So if I do direct substitution again and take this 2 value and plug it in now, I would get 2 plus 2, which equals 4. So my limit does exist. If I was going to graph this, by the way, if you were going to graph this function, it would look like this. Has a y-intercept at 2, a slope of 1, and at 2 there happens to be a hole in the graph. So it looks like this. And that came from this, the x plus 2. And so this is the line that came from getting rid of that hole, so we know the hole is there, but other than that, it looks like the function x plus 2. And then down here, the second part of it says that the function equals 1 when x equals 2. So there should be a point at 1 when x equals 2. So this is what the graph of this piecewise function looks like. Now let's answer these questions. Question 1, f has a limit at x equals 2. Yes, f does have a limit at x equals 2. The limit is 4. We just discovered that right here. Question 2, f is continuous at x equals 2. Nope, it's not continuous because the function does not equal what the limit equals. Therefore, there's a big hole in the graph, and I would have to lift up my pencil in order to draw this. So no, it's not continuous. And we already know that automatically if it's not continuous, then it's not differentiable either, because a train would derail if there's a giant hole in the track. So the only one that was true was 1, 2, and 3 are not true statements. Therefore, the answer is A, 1 only. For this one, it's very similar. The only difference is that this one is a breaking point. It's not a hole in the graph. So one thing is happening on one side of 3 and something else is happening on the other side of 3. So I could graph this if I wanted to, but the only reason I graphed it on the last one was to kind of show you the visual of what it looks like. On this one, if you want to graph it, I'll let you go ahead and do that on your own. But just for the purposes of answering this question, let's see how we would do that. So For the first one, to find out if the limit exists at 3, we would plug in 3 to both the top and bottom function so that we can see what the function is going to from both sides. So if I plug in 3 to the top, I get 3 plus 2, which is 5. If I plug in 3 to the bottom, I get 4 times 3 minus 7, which is 12 minus 7, which is also 5. So yes, the limit does exist at 3. If the limit exists here and we know the function is also equal to this, because right here it says x is less than or equal to 3, so it's also equal to 5 at that point. Therefore, it is continuous as well. And then to figure out if it's differentiable, we have to take the derivative, of both the top and bottom. So we would say f prime of x is equal to, the derivative of x plus 2 would just be 1 plus 0, so 1 when x is less than or equal to 3. And the derivative of 4x minus 7 is just 4 when x is greater than 3. And because 1 and 4 are different numbers, the derivative coming in from the right-hand side, from the left-hand side is 1, the derivative coming in from the right-hand side is 4. Therefore, this is not a nice smooth connection because the derivatives are not equal to each other. Therefore, it is not differentiable at x equals 3. So the only correct answers are 1 and 2. For this one, it says let f be the function defined above, where c and d are constants. If f is differentiable at x equals 2, what is the value of c plus d? So remember, in order for a piecewise function to be differentiable, it has to also be continuous. So let's plug in the breaking point to both of these, and we're going to force them to be equal to each other. So if I plug in 2, I get, oops, too far. If I plug in 2, I get 2c, try that one more time, there we go, 2c plus d, for the top function. I just plugged in 2 for x. And I'm going to force that to be equal to the bottom function at 2. If I plug in 2 for this, I get 2 squared is 4, minus c times 2 would be 2c. Now I can simplify that a little bit. I'll bring the 2c over to this side. So 2c plus 2c would be 4c plus d is equal to 4. So this is my function that's going to help me prove continuity. But I don't obviously know what c and d are yet. So now I need a function that's going to help me prove differentiability. So I need to take the derivatives of both top and bottom in this example. So f prime of x is equal to the derivative of the top function, cx plus d would just be c, because d is a constant, its derivative would be 0, and then c is a constant multiple, and the derivative of x is 1. So that's for x less than or equal to 2. And for the bottom one, the derivative of this would be 2x for the x squared, 2x. And then right here, the derivative of negative cx would be negative c. So 2x minus c when x is greater than 2. And again, I'm going to plug in the breaking point and set these equal to each other. So if I get the breaking point plugged in, I get c is equal to, if I plug in 2 here, I get 2 times 2, which is 4, minus c. And we're down to one variable now in this equation, so I can actually solve this equation for c. If I add c over to the other side, I get that 2c is equal to 4. And if I divide 2 on both sides, I get that c is equal to 2. So I'm going to use that, and I'm going to plug it into this equation so that I can solve for d. So if I plug in 2 here, I get 4 times 2 is 8. 8 plus d equals 4. Therefore, d is equal to negative 4, because 4 minus 8 is negative 4. So those are the values for c and d, and the question is saying what is the value of c plus d? So essentially, what's the value of positive 2 minus 4, which is negative 2? And that is answer choice B. Negative 2 is the value of c plus d. For this one, it says the graph of the function f is shown in the figure above, and it has a vertical tangent at the point 2, 0. So, oops. I always go so fast, don't I? Try that again. It has a vertical tangent at the point 2, 0. So right here, there's a vertical tangent line. All right, so keep that in mind. It has horizontal tangents at the point 1, -1. So right here, there's a horizontal tangent line. And at 3, 1, right there, there's a horizontal tangent line. It says for what values of x is f not differentiable? So remember some of the reasons we talked about a function not being differentiable would be if there's a corner, I don't see any corners. If there's a cusp, I don't see any cusps. if there's a vertical tangent line, so we just said that 2 gives us a vertical tangent line, so this is one of the points where it's not differentiable. And then last but not least, if there is a discontinuity, and the only point that I see that's a discontinuity is at 0, because there is a jump discontinuity. So this graph is not differentiable at 0 as well as at 2, and that's answer choice B, at 0 and 2. And the last problem for this section says the graph of f is shown in the figure above. Which of the following could be the graph of the derivative of f? So remember that derivatives, wherever there is a horizontal tangent line, the derivative should be 0. So I know on this graph right here, there's a horizontal tangent line right about here. All right. So the derivative, whatever derivative it is, should have a 0 around this point. So if we look here, like on the graph of A, it has a 0 there, so it could be that one. On the graph of B, it does not have a 0 there, so I'm guessing it's not B. On the graph of C, yes, it has a 0. On the graph of D, it's missing that 0, so I'm guessing it's not D. And on the graph of E, it does have that 0 as well, so it could be that one as well. Now, other things, I'm going to start talking about other things we should be looking for. This is a linear function. E is a linear function. So remember that the derivative being linear meant that the equation right above it, the original function, was probably quadratic, or not probably, is quadratic, because in order for the derivative to be linear, the original function must have been quadratic. But this is not a graph of a quadratic function. This looks more like a trig function, so I'm guessing E is not going to be our derivative either. So now we're down to A and C, which do look like trig functions, so it makes sense that its derivative would also be a trig function. So now let's pay attention to the slopes. Notice how this function is increasing, 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 increasing up until here. That means that its derivative, or its slope, is positive, 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 positive up until here. After that, it's negative, 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 because it's decreasing the whole time. So I'm looking for which one of these has positive values and then changes after the 0 to have negative values, and that one would be answer choice A. Notice that these are all positive because these are all above the x-axis. And after the x-axis, they all change to being negative values because they're all below. Just like here, it was increasing. The increasing relates to the positive values. And after the maximum, it was decreasing. And the decreasing relates to the negative values. So the correct answer here would be answer choice A. That's the only one that matches. And now we've made it to the next section, so that's it for the first video, and we'll start a new video for this section.